and welcome to lecture number 2. So in this lecture we are going to work on some problems which is going to apply the binomial theorem. So we can say this is going to be an application based problem. So let us begin. So this is our first question, which asks which one is larger, 1.01 raised to the power of million or 10,000. Okay, it's a wild guess. We can say that 1.01 it's raised to the power of 1 million, which is a very big number, so might seem that this is a very big one. Let's see. Let's do it with the help of a binomial theorem. So we'll it by writing 1.01 raised to the power of 1 million. Now 1.01 can be rewritten as 1 plus 0.01 raised to the power of 1 million. Now we expand it using a familiar binomial theorem. So we have 1 million C0 1 raised to the power 1 million times 0.01 raised to the power of 0 plus 1 million C1 and 1 raised to the power of 999,999 times 0.01 raised to the power of 1 and the remaining terms. So we'll write down the other positive, the remaining positive terms. So 1 million C0 is 1. 1 raised to the power 1 million is also 1. And anything raised to the power 0 is 1, as we already know. The 1 million C1 is 1 million times 1 times 0.01 plus the other terms, the remaining terms. Now we have 1 here in the first term, then 1 million times 0.01 gives us 10,000 plus the remaining terms. So 10,000 plus 1 is 10,001 plus remaining terms. So this is the value of 1.01 raised to the power of 1 million. Now what we are going to do is we have to compare with it 10,000. Now let me write 1 million. Okay, so you can see I have already got 10,001 and there's still other terms remaining which we haven't added yet, but if we happen to take few more cases, then it's clear, it's evident that this number is greater than 10,001. Hence we can say that 1.01 raised to the power of 1 million is greater than 10,000. So this was the first question. Okay, so let's do another one. Question number 2 asks which one is larger, 1.1 raised to the power 10,000 or 1,000. It's very similar to the first one, so this is how we're going to do. So we first write down 1.1 raised to the power of 10,000 as 1 plus 0.1 raised to the power of 10,000. Then we're going to expand it using a binomial theorem. So we have 10,000 C0 1 raised to the power of 10,000 is 1, so I'm skipping it, and then we have 0.1 raised to the power of 0 plus 10,000 C1, then we have 0.1 raised to the power of 1 plus some other positive some other, or you can say the remaining positive term, some other positive terms. Now 10,000's C0 is 1, 1 times 1, 0 to 0.1 raised to the power of 0 is always 1, so the first term would give us 1. Then we have 10,000, which is the value of 10,000 C1 times 0.1 plus the remaining terms. So when we add the first term to the second term, so we should get 1001 plus the remaining terms. We can check it out. The second term is 10,000 times 0.1 is 1000, so 1000 plus 1 gives us 1001. So we have the 1001 plus the remaining terms. Then we use the same logic. We can say that when we are to compare with 1000, we are already getting 1001. 1000, and when we add more terms to it, it's definitely going to be greater than 1000. Hence 1.1 raised to the power of 10,000 is greater than 1000. That's it. So this is done. Let's do the third problem. This is also similar to question number 1 and 2. So here we have to find out which one is the larger number, 1.2 raised to the power of 4000 or 800. Let's check it out. Solution. So we'll start with 1.2 raised to the power of 4000 and rewrite it as 1 plus 0.2 raised to the power of 4000. Then we expand it, then we should get 4000 C0. We do not have to write the other terms because it's going to be 1. Now we have 4000 C1. Then we have 1 raised to the power of 3999, so which is always 1. I'm not writing it again. So we have 0.2 raised to the power of 4000. This time let me write down the third term as well. So we have 4000 C2 0.2 raised to the power of 2 plus the remaining terms. So the first term is going to give us 1. 4000 C1 is 4000 times oh, I made a mistake here. This is not 4000. This is simply 1. My bad. So this is times 0.2. Now 4000 C2 is going to be oh, that's a very big number. Wait, let me grab my calculator. 4000 so we have 4000 combination 2 is it's a very big number. So this is 7,998,000 times 0.04 plus ... So we have 1 plus 800 plus, now should we multiply? Let's leave it because it's going to be a very huge number. So we already know it's a very big number. It's greater than 800. So we just write here other terms. The first term and the second term was more than enough. It was sufficient to prove that it is greater than 800 and 800 because we are getting 801 plus the other terms. Okay, so using similar logic, we can say 1.2 raised to the power of 4000 is greater than 800. Okay. In this question, we are asked to prove that 101 raised to the power of 50 is greater than the sum of 100 raised to the power of 50 plus 99 raised to the power of 50. Okay, so let's do that. So we're going to make an assumption here. So we're going to consider 101 raised to the power of 50 to be equivalent to x, and y is equals to 100 raised to the power of 50 plus 99 raised to the power of 50. Now what we're going to do is we're going to do x minus y. So that should give us 101 raised to the power of 50 minus 100 raised to the power of 50 minus 99 raised to the power of 50. Okay, now we're going to rewrite it. Instead of writing 101, we're going to write it as 100 plus 1 raised to the power of 50. I'm going to in the second term I'm going to rewrite it as, I'm going to use the third term in the second term. I should have written it before, so I'm going to write it here as 100 minus 1 raised to the power of 50. And I'm writing the second term in the third term in this particular case, so no changes here. Now what we're going to do is going to expand this. So this is 50c0 100 raised to the power of 50. We don't have to worry about the second term since that is 1. It's always going to be unity. Then we have 50c. Okay, I just remember what we can do here. So this is actually equivalent to the conclusion drawn from the binomial theorem. So we have x plus a raised to the power of n minus x minus a raised to the power of n can be written as 2 times 50c1. So we have 100 raised to the power of 49 plus 50c3 100 raised to the power of 47 plus ... the last term will be 50c49 100 minus 100 raised to the power of 50. Now we open it up. The 50c1 is going to give us 50 times 100 raised to the power of 49. Now we're not going to make any changes. We'll leave 50c3 the way it is. It's simply 100 raised to the power of 47. 50c49 is 50. Yeah, that's 50. So 50 times 100 minus 100 raised to the power of 50. Now we're going to distribute this 2. So this is 2 times 50. So this is going to give us 100. 100 times 100 raised to the power of 49 plus 50c3. 2 times 100 raised to the power 47 plus the last term, which is 2 times 50 is 100. This is going to be 100 times 100 minus 100 raised to the power of 50. Scroll down this. So 100 times 100 raised to the power 49. So what we can do, we can add the powers, the indexes. That should give us 50. This will become evident very soon. So let me quickly rewrite this. So 2 times 100 raised to the power of 47 plus 100 times 100 is 100 squared minus 100 raised to the power 50. So this was done so that we could cancel this 100 raised to the power 50, the last term and the first term. So the last term and the first terms cancels out. So this was x minus y. So we have 50c3 2 times 10 raised to the 100 raised to the power of 47 plus the last term will be 100 squared. Now you can see these are all positive terms. Now what I mean to say is, like, when we add them up, we are always going to get a value which is going to be some positive non-zero value, which suggests that x minus y is always greater than 0. Now if x minus y is greater than 0, then we can transpose the y to the left hand side, then that means that x is greater than y. Now what our initial assumption was that x is 101 raised to the power of 50 and y is the other two terms. So we can say 101 raised to the power of 50 is greater than 100 raised to the power of 50 plus 99 raised to the power of 50. Yes. So this is how we can prove this particular question with the help of binomial theorem. This is another proving question. So this question asks us to prove that 9 raised to the power n plus 1 minus of 8 of n minus of 9 is always divisible by 64, provided n is a positive integer. So in order to solve, or in order to prove a question like this, we'll start with 9 raised to the power of n plus 1, and we're going to rewrite it as 1 plus 8 raised to the power of n plus 1. Then we expand it using the binomial theorem. We have n plus 1 c0, so we have 1 raised to the power of n plus 1, which is 1, times 8 raised to the power 0, which is 1. The second term will be n plus 1 c1, so this is simply going to be 8 raised to the power of 1. Then we have n plus 1 c2 8 squared plus dot, and the last term would be n plus 1 c n plus 1 8 raised to the power of n plus 1. Then the first term would be 1. The first term is not 1, this is n plus 1. The first term is n plus 1 plus I was correct. n plus 1 c0 is always 1. My bad. This is n plus 1. This is n plus 1 times 8 plus. Now what we're going to do, we're not going to open up the coefficient. Instead we're going to take 8 squared as the common factor. Then the third term would become n plus 1 c2 plus the fourth term would become n plus 1 c3. It was 8 cubed, so we have already factored out 8 squared, so what we'll be left with is 8. N plus 1 c n plus 1, which is the last term. So since we have taken factored out 8 squared, so we'll be left with 8 raised to the power of n minus 1. Okay, so let's solve it. So this is 1 plus 8n plus 8, which is going to give us 8n plus 9 plus 8 of squared is 64, n plus 1 c2 plus n plus 1 c3 times 8 plus dot, and what we'll be left with, n plus 1 c n plus 1 is always 1, so we have 8 n minus 1. 9 raised to the power of n plus 1. Now we're going to bring few of the terms from the from the right hand side to the left hand side. So that's what we get. This is equals to 64. Now this entire terms is some positive number. We really don't have to worry about the answer here. Now this actually proves this is done. So in this question we have to prove that 6n minus 5n, when this is divided by 25, it leaves the remainder 1. So let us begin. So we start by considering 6 raised to the power of n and rewrite it as 1 plus 5 raised to the power of n. Then we're going to expand it using the binomial theorem. So this is nc0. So the first term is always nc0. Then we have nc1, 5 raised to the power of 1, plus nc2, 5 squared, plus nc3 5 cubed plus the final term ncn 5 raised to the power of n. Then we're going to open the coefficient. So this is 1, this is n times 5, so which is going to be 5n plus nc2. So we're not computing the value for nc2. Instead, what we're going to do is we're going to factor out 5 squared. So this is going to leave us with nc2 plus nc3 times 5 plus the final term is ncn is always 1, so we have 5 raised to the power of n minus 2, which is equals to 5 of n plus 1 plus 25. So this entire term within the parenthesis is going to be some positive value. So we transpose the 5n to the left hand side. We're left with 1 on the right hand side plus 25. Let's call this some positive value. Let's denote it by alpha. Alpha is this positive value. So this is proved. So when we divide 6 raised to the power minus of 5n by 25, we get the remainder 1. This is followed from the Euclid's division lemma. So this is proved. In this question, it is given that a and b are distinct integers. Then we have to prove that a raised to the power of n minus b raised to the power of n is always divisible by a minus b, where n is a natural number. Okay, so to do this problem, what we have to do is we need to start with a raised to the power of n, and then we are going to rewrite it as a minus b plus b raised to the power of n, and then we are going to expand it using the binomial theorem. So the first term will be nc0 a minus b raised to the power of n plus nc1 a minus b raised to the power of n minus 1 times b plus ... Then we take the second last term, which is nc n minus 1. So this is a minus b to the power of 1 raised times b raised to the power of n minus 1 plus the last term, which is ncn b raised to the power of n. Now nc0 is always 1, so here we have a minus b raised to the power of n plus the second term is nc1, which is always n, times b times a minus b raised to the power of n minus 1 plus ... The second last term is nc1 n minus 1. So what is nc n minus 1? Nc n minus 1 is equals to n factorial over n minus 1 factorial times n minus of n minus 1, which is 1 factorial. So this is n times n minus 1 factorial divided by n minus 1 factorial. So they cancels out, leaving us with n. So instead of writing here ncn, I'm going to write it as n times a minus b times b raised to the power of n minus 1 plus ncn is 1. So we have b raised to the power of n. This is a raised to the power of n. So this b, I'm going to take it to the left hand side. So we have a raised to the power of n minus b raised to the power of n. This is a equals to a minus b raised to the power of n plus n times b times a minus b raised to the power of n minus 1 plus dot 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 plus n times a minus b times b raised to the power of n minus 1. Now what we're going to do is we're going to factor out a minus b. Then the first term would be a minus b raised to the power of n minus 1. Since we have taken 1 and a minus b out, we have factored it out, so there's one term less, so this is n minus 1 plus n times b times a minus b raised to the power of n minus 2. The final one, we already have an a minus b, so that gets factored out, so we'll be left with n times b raised to the power of n minus 1. So this is the expression for a to the power of n minus b to the power of n. Now we can clearly see that okay, let's assume that this is going to be what was a and b? It's given that a and b are distinct integers, so whatever be it is going to be some constant value, so let's denote it by alpha. So what we get is a raised to the power of n minus b raised to the power of n is equals to a minus b times alpha. So that's done. We are asked to prove that a raised to the power of n minus b raised to the power of n is divisible by a minus b. So this clearly says that this is divisible by a minus b, the term on the left hand side. That's proved.